So, if the tiny cycloidal disc inside a robotic surgical arm is manufactured just like 4 microns off spec, the robot doesn't just vibrate slightly. It actually misses the incision entirely.
Right. Yeah, and that's exactly why precision on that level isn't, magic. It's this incredibly brutal, unforgiving process of communication and verification.
Which is exactly what we're looking at today. Welcome to the deep dive, everyone. We're translating some highly technical manufacturing vocabulary into the absolute physical realities of the factory floor. Because, how do you prevent those catastrophic failures?
Well, it starts before the metal is even cut. You need a foolproof way to communicate the design, which brings us to GD&T.
Right, geometric dimensioning and tolerancing. But, I mean, I have to push back here a little bit. Why do we need an entirely separate language of symbols for this? Like, if a hole needs to be a 1/4 inch wide and straight down, can't the designer just write that in text on the blueprint?
You'd think so, right? But straight down is highly subjective in manufacturing. So GD&T doesn't just control the size of a feature. It actually controls the exact geometric relationship between features.
Oh, okay. So it's not just about how big the hole is.
Exactly. It mathematically dictates exactly how perpendicular that pinhole must be relative to a specific datum surface, regardless of where it's positioned. So it locks down the acceptable variation of the shape itself.
Okay, so it acts like a strict mathematical constitution for the part.
That's a great way to put it, actually. But once the machinist cuts that metal, you need to prove it matches the GD&T. And that's where you bring in a CMM, a coordinate measuring machine.
Right. And our sources mention using a CMM to scan that cycloidal disc we talked about to verify a profile deviation within 3 microns. Now, I know 3 microns is microscopic, but realistically, how do you even measure that accurately when ambient heat from the machinery is constantly expanding the metal?
Yeah, that is the real nightmare scenario right there. I mean, you can't just drop a CMM next to a hot lathe. They acquire these precise 3D coordinates using highly sensitive probes, but they usually have to operate in strict climate-controlled labs.
Wait, really? Just because of the temperature?
Oh, absolutely. The software actually has to calculate and compensate for the thermal expansion coefficient of both the part and the measuring stylus itself, just to verify that 3-micron profile.
Wow. Okay, so we've locked down the macro geometry in a cold room, but if this shaft is going to be spinning at like 10,000 RPM, a perfect shape isn't enough, right? We have to zoom in on the micro texture.
Precisely. And that brings us to surface profilometry. It's the measurement of the microscopic topography of the metal. So we're checking on raw value to confirm we've hit a mirror-like finish.
Why does a mirror finish actually matter mechanically, though? Is it just to lower the friction coefficient between parts?
It's friction, yeah, but also fluid dynamics. If the raw value is too rough, those microscopic peaks literally break through the oil film and grind against the opposing part.
Oh, yikes. Catastrophic wear.
Exactly. But ironically, if it's too smooth, the surface won't retain the lubricating oil at all, so it's this massive balancing act.
Fascinating. Okay, so the texture is dialed in, but what happens when we spin that shaft up to operating speed? The notes bring up runout, which is variation relative to an axis during rotation. We're basically talking about dynamic wobble here.
Runout is exactly that. It's eccentricity. The shaft might measure perfectly round on the bench, but if its center of mass doesn't align flawlessly with the theoretical axis of rotation, you get radial runout.
So it's essentially the engineering term for a wobbly shopping cart wheel, but happening at thousands of RPMs.
Yes. And at those speeds, that periodic vibration will shatter the surrounding bearings in hours, if not, minutes.
All right, so let's say the part passes the CMM, the profilometer says the ray value is perfect, and there's 0 radial runout. We're totally good to go.
Wait, not necessarily.
Wait, what else could there be?
Well, the geometry might be perfect, but the extreme heat from the manufacturing process itself might have secretly weakened the metal.
Ah, okay. The sources call out needle etching here to detect grinding burn. But I'm kind of stuck on the mechanics of this. How does a chemical etch reveal thermal trauma?
So when you grind hardened steel, localized friction generates intense heat. And if it gets too hot, it alters the crystalline structure of the metal, essentially retempering or softening that specific microscopic area.
Oh, I see.
Yeah, so needle etching uses a mixture of nitric acid and alcohol. The acid reacts differently to the softened, damaged grain structure than it does to the hardened steel.
So it basically acts like a polygraph test for the metal, or actually it's like using a blacklight at a crime scene. The gear tooth looks flawlessly shiny to the naked eye, but the acid chemically stains the damaged molecules dark, exposing a hidden burn scar.
That is a perfect visualization. It exposes metallurgical realities that physical geometry checks just fundamentally cannot see.
That paints such an incredible picture. We are stacking tolerances from the mathematical rules of GD&T, navigating the fluid dynamics of surface profilometry, surviving the forces of runout, and then finally verifying molecular integrity with nidal etching.
It really reframes what it means when we say a machine runs smoothly. It's heavily engineered illusion built on ruthless verification.
It really is. And, on that note of ruthless verification, I want to leave you with a paradox to chew on. If our verification tools, like those climate-controlled CMMs, have to be exponentially more precise than the complex parts they measure, how do engineers manufacture and calibrate the CMMs themselves? What measures the measure? Think about that the next time you push a button and expect perfection.